The most ruthless hunters in Earth's history aren't the animals you think they are. The fossil record preserved something more complicated. Tyrannosaurs biting the faces of their own kind, apex predators consuming their own dead, herbivores driving permanent wounds into predator bone. Tonight we go through 10 cases, one by one, and read what the bones actually say. There is a skull sitting in a museum in South Dakota called Stan. Named after the amateur paleontologist who found it in 1987, Stan is one of the most complete T-Rex specimens ever recovered. Roughly 70% of the skeleton intact, including a skull that has been studied more closely than almost any other dinosaur fossil on record. The excavation took 5 years, and the preparation work that followed took several more. The resulting skeleton has since been cast and distributed to institutions around the world, making it a reference point for almost every serious anatomical study of T-Rex conducted in the last 3 decades. Most people who look at it see what they expect to see: the iconic predator. The largest land carnivore of the late Cretaceous, the animal that has anchored every popular understanding of dinosaur life since the first full skeleton went on display in 1905. The jaw is 1.5 meters long. The animal itself ran between 12.3 and 13 meters from snout to tail, and at the rear of that jaw sat a bite capable of crushing bone outright, not just cutting through flesh. In life, T-Rex held its body roughly horizontal, the massive skull counterbalanced by the tail, moving on hind limbs powerful enough to cover several meters per stride. The eyes face forward, a configuration associated with depth perception and active predation, giving the animal overlapping fields of vision across a wide arc in front of it. T-Rex lived in what is now the northern Great Plains during the final few million years of the Cretaceous, in a landscape of coastal river floodplains, wetlands, and coniferous forest cut through by seasonal waterways. The climate was warm and humid. Hadrosaurs and ceratopsians moved through that landscape in large numbers, and for most of the 20th century, the scientific consensus placed T-Rex at the unchallenged top of the food chain that fed on them. Stan looks, in other words, exactly like what a century of natural history has said T-Rex was: the apex of the apex, an animal with no serious threat from anything in its ecosystem. That assumption held for a long time. Then, researchers looked more carefully at the back of the skull. But here is the problem with the Stan skull, and with the entire century of assumptions that surrounded it. The puncture wounds on the back of the head don't match any prey animal in the late Cretaceous ecosystem. The shape is wrong for a hadrosaur. The dimensions rule out ceratopsian horns. The placement, the back of the skull, not the snout or the flanks, is inconsistent with any defensive wound an animal receives while attacking something it intends to eat. But the wounds are perfectly shaped. They are clean, deep, bilateral, and they match T-Rex teeth exactly in both size and spacing. There is only one animal in the Hell Creek Formation with a jaw large enough to produce marks like that. And every time researchers checked the dimensions against the available specimens, the spacing kept matching the same thing. The wounds on Stan's skull weren't decorative scars. They were healed completely over months, which means the animal was bitten by another T-Rex, survived the attack, recovered inside the same environment that produced the animal that bit it, and kept going. That detail alone dismantles the standard picture, but the full account is harder to ignore. 324 catalogued face wounds across multiple specimens, a bite force at the rear of the jaw capable of producing somewhere between 5.5 and 6 tons of pressure, and feeding marks found on toe bones, bones with almost no usable meat on them. You strip a skeleton that far down, only when nothing can be wasted. T-Rex wasn't just an apex predator operating above the food chain in comfortable solitude. The bone record says it was an animal that bit the faces of its own species regularly enough to leave a pattern, consumed the carcasses of its own kind when conditions demanded it, and operated inside a social hierarchy written entirely in scar tissue. The version of this animal that has existed in popular imagination for the better part of a century, the lone giant, the unchallenged ruler, doesn't survive contact with what the fossils actually say. T-Rex was not alone in this. Elsewhere in the Tyrannosaur family, a single specimen told a more complete story than anyone had expected a lone skeleton to contain. Daspletosaurus doesn't get the attention T-Rex gets. It's smaller. It lived roughly 75 to 77 million years ago in what is now Alberta, and it shares the Tyrannosaur family tree without carrying the same cultural weight as its more famous relative. First described by Dale Russell in 1970 from material recovered in what is now Dinosaur Provincial Park, it entered the literature primarily as a data point in the story of Tyrannosaur evolution, a step in a lineage rather than a subject in its own right, and the limited number of known specimens meant there wasn't much pressure to treat it otherwise. Alberta in the late Cretaceous was a low-lying coastal environment bordering the western interior seaway, a landscape of river channels, dense floodplain vegetation, and extensive wetland systems that supported enormous herds of hadrosaurs and ceratopsians. Daspletosaurus occupied the apex predator role in that ecosystem, a deep-skulled, muscularly built tyrannosaur with the same forward-facing eyes and powerful hind limbs that characterized the family, capable of taking the large prey animals that moved through the wetlands in numbers. In basic body plan, it resembled T-Rex closely, bipedal, heavy through the neck and skull, lighter through the forelimbs, but sat noticeably smaller and carried proportionally longer arms than its more famous descendant. It was a serious predator, well within the size range capable of taking large hadrosaurs and ceratopsians, but paleontologists spent decades treating it primarily as context for understanding how tyrannosaurs evolved toward T-Rex, rather than as a subject worth examining on its own terms. That changed when a single specimen was analyzed in detail. The fossil record for Daspletosaurus is not extensive. There aren't many individuals to compare, which makes what was found in the available specimen more striking rather than less, because what was found wasn't just evidence of what this animal hunted. It was evidence of what happened to this animal during its own lifetime, written across its face and preserved across its bones, telling a story that no one had expected a single skeleton to contain. But the wounds on the Daspletosaurus specimen don't read as a single event. A lone confrontation, a territorial dispute, a failed hunt, one bad encounter leaves a particular signature in bone, localized damage, one episode of healing, a discrete scar. What the Daspletosaurus face shows is something layered. Injuries at different stages of healing, some older and more fully remodeled, others fresher, indicate that the attacks happened across a span of time. This animal wasn't ambushed once. It was targeted repeatedly across what appears to have been a sustained period of its adult life. But there is a second problem, and it sits in a completely different part of the skeleton. The post-mortem bite marks carry a different tooth spacing, a different bite geometry, the signature of a jaw that doesn't match the one responsible for the facial wounds. The same skeleton carries two distinct patterns of damage from two different sources at two different points in its story. What the single Daspletosaurus specimen gives you is a complete life story compressed into one skeleton. The healed wounds are the first chapter, repeated biting across the face during the animal's lifetime, the kind of sustained damage that points to regular intraspecific aggression rather than a single encounter. The animal didn't just get bitten once and flee, it was bitten, healed, and returned to whatever social situation produced the biting in the first place. But the post-death bite marks tell the second chapter, and they're different in pattern from the healed wounds. A different jaw, a different angle, a different animal feeding on the carcass. Both ends of certain bones were chewed, which means the feeding was thorough. The frontal teeth in Tyrannosaurs were built for piercing. The rear teeth were built for holding. At 8 to 9 meters and around 2.5 tons, Daspletosaurus was not something easily pushed around by accident. And the skeleton says it still spent its life under sustained attack from members of its own species, survived long enough for those wounds to heal multiple times, and died in a way that gave whatever found the body full access to it. There was no clean exit. Life and death both belonged to the same species. That was one individual. What the Gorgosaurus sample gives you isn't one case. It's a pattern spread across adult Tyrannosaur skulls, appearing in the same locations every time. Consistent enough that the standard explanations for how large predators injure each other couldn't account for what the sample was showing. For most of paleontology's history, bite wounds on dinosaur skulls were treated as isolated incidents, injuries from prey, or occasional confrontations between rivals, or simply the hazards of living in a world with large teeth. When a specimen came in with facial damage, researchers noted it, catalogued it, and moved on. The assumption was that combat in large theropods was rare enough to be considered exceptional, the kind of event that left a mark precisely because it didn't happen often. Gorgosaurus is a tyrannosaur from roughly 76 to 77 million years ago, lighter and faster than T-Rex at around 8 to 9 meters and roughly 1 ton. Built for pursuit across the floodplains of what is now Alberta, rather than for raw, crushing power. It hunted the large plant eaters that moved through its formation in numbers, occupied the apex predator role, and left a fossil record extensive enough to allow researchers to examine multiple adult skulls side by side. When they did that comparison, when they looked at adult skull after adult skull and mapped the location and nature of the wounds, the isolated incident interpretation stopped being available. But the location of the wounds was not random, and that is what changed the interpretation entirely. Injuries from prey animals cluster where prey can reach: the snout, the lower jaw, the front of the skull, places that make contact during a hunt. Injuries from rival predators in territorial disputes tend to be opportunistic, scattered across whatever surface was accessible during the confrontation. Neither of those patterns describes what researchers found across the Gorgosaurus sample. The wounds concentrated around the eye sockets, the upper snout, and the lateral jaw, areas that require deliberate, targeted biting from the front of another animal's skull. But the detail that made the territorial dispute explanation untenable wasn't the placement alone. Subadult Gorgosaurus specimens don't show this damage. Juveniles don't show it. The wounds begin appearing at a specific point in the animal's development, and they don't appear before that point consistently across the entire sample. 60% is not a rare finding. It is not an edge case or an outlier population skewed by unusual preservation. 60% of adult tyrannosaur skulls showing bite wounds in the same locations. Concentrated around the eye sockets, the snout, and the jaw is the majority of the sample, and the consistency of the placement is what makes it meaningful. Random aggression doesn't produce that kind of pattern. Random aggression leaves marks wherever teeth happen to land. These marks are clustered, and they begin appearing at sexual maturity, which points to a single explanation. Face biting was how tyrannosaurs established mating hierarchy. The face was the target. The hierarchy wasn't communicated through display or sound or any behavior that left no trace. It was communicated through teeth applied directly to the skull, and it was repeated often enough that the majority of adults carried the evidence of it for the rest of their lives. Tyrannosaurs bit the faces of their own kind, and the pattern is in the bone. From late Cretaceous Alberta, the next case moves to Madagascar, where a different predator left evidence that required a forensic elimination process to confirm, testing every other predator in the formation before the evidence could name the animal responsible. Madagascar in the late Cretaceous was not a lush environment. The Mahajanga Basin, where the most significant fossils from this period have been recovered, preserves evidence of a semi-arid landscape with extreme seasonal variation, periods of relative abundance followed by periods of severe scarcity. Channel sandstones and floodplain mudstones in the formation record an environment of seasonal rivers that swelled during wet periods and contracted sharply during dry ones, leaving the fauna concentrated around shrinking water sources for months at a time. The fauna that lived there adapted to those conditions over millions of years, and the predators at the top of the food chain were no exception. Majungasaurus was the dominant large theropod in that formation, 6 to 7 meters long, over 1,100 kilograms, with a skull built for powerful biting and a tooth replacement rate that set it apart from every other carnivorous theropod so far discovered. It belonged to the Abelisaurid family, a group of theropods characterized by unusually short, deep skulls and forelimbs so reduced they were effectively vestigial, far smaller relative to body size even than T-Rex's arms. A single blunt horn rose from the top of the snout, and the skull surface carried a rough, heavily textured bone that was unusual even by theropod standards. In life, it moved exclusively on powerful hind limbs, the tiny forelimbs playing no meaningful role in predation or locomotion, the mass of the body concentrated in the skull and torso. The sauropods and smaller vertebrates that shared the Mahajanga Basin with it were the assumed prey base, and before the key analysis, the prevailing picture of Majungasaurus was of a conventional apex predator operating within the standard constraints of its ecosystem. Most theropods replaced their teeth gradually on a slow cycle. Majungasaurus replaced them at a pace researchers had not seen in any other carnivorous dinosaur, an adaptation the leading explanation suggested to regularly contacting something hard enough to wear the dentition down at that rate. What they needed to determine was whose bones were responsible for that wear, but identifying a likely candidate and proving it are not the same thing, and the Mahajanga Formation presented a genuine problem. Madagascar, in the late Cretaceous, was not a species-poor environment. Multiple predators occupied the formation alongside Majungasaurus, each with its own tooth morphology, each leaving a potentially distinct signature in bone. The bite marks on the specimens weren't simple punctures. They were parallel scratches left by serrated tooth edges dragging across bone surface, and the spacing between those scratches was measurable. But measuring something is only useful if you have a reference to compare it against. Researchers had to reconstruct the tooth geometry of every predator in the formation and test each one against the evidence. Some were eliminated quickly, their tooth spacing too wide or too narrow, their serration pattern inconsistent with what the marks showed. Others required closer analysis. The process was methodical and slow, and it left the question open longer than the initial evidence suggested it should, with no confirmed match yet, and every remaining candidate requiring the same level of scrutiny before it could be ruled out. The reason this case holds up scientifically is that the researchers didn't work from assumption. They worked from elimination. Every predator present in Madagascar's Mahajanga Formation was tested against the bite mark evidence. The spacing between scratches was measured under microscope against the serrated edges of every known tooth in the ecosystem. One by one, the other predators were ruled out until the only match remaining was Majungasaurus itself. The tooth that made the marks belonged to the same species as the bones being eaten. That is the court-level standard the researchers applied, and it held. But the tooth replacement rate is what takes the finding further. A full new dentition roughly every 2 months, 13 times faster than most other carnivorous theropods, is not a neutral biological fact. That rate of replacement is consistent with constant, sustained bone contact, the kind that wears teeth down fast enough to require continuous regrowth. Majungasaurus wasn't eating its own kind occasionally during famine cycles. The biology of its jaw says regular bone consumption was built into its normal existence, and the evidence says it preyed on whatever was available, including itself. Madagascar gave researchers the first forensically confirmed case of dinosaur cannibalism, built on elimination rather than assumption. From that formation, the next site is a quarry in Jurassic Colorado. Nearly 2,400 bones recovered across decades of excavation, and what the bite mark distribution across those bones says about the animals that were still alive when the food ran out. The Migatmore Quarry in western Colorado has been actively excavated since 1981, and by any measure, it is one of the most productive late Jurassic fossil sites in North America. The site was discovered by Pete and Marilyn Miggott and J.D. Moore, amateur fossil enthusiasts, and has been worked primarily by the Denver Museum of Nature and Science across more than 4 decades of systematic excavation. The rock there dates to roughly 150 million years ago. The Morrison Formation, a geological unit that has produced more dinosaur material than almost any other deposit on Earth. The Morrison landscape of what is now western Colorado was a broad semi-arid floodplain system cut through by seasonal rivers that swelled during wet periods and contracted to isolated pools during the dry season. Conifers and tree ferns lined the watercourses, with open terrain between them, and the ecosystem supported an extraordinary range of large animals. Sauropods, among the heaviest land vertebrates that had ever lived up to that point, alongside ornithopods, stegosaurs, and the predators that hunted them all. Allosaurus is the dominant large predator at the site, a 7.5 to 9 meter animal, 1.4 to 2 tons, built around a slashing bite rather than a crushing one, with a skull designed to deliver fast, repeated strikes rather than sustained jaw pressure. In life, it carried distinctive bony ridges above the eyes, lacrimal crests that gave the skull a recognizable silhouette, three-fingered hands bearing large curved claws, and hind limbs proportioned for speed across open terrain. The quarry has yielded 2,368 individual bones across decades of excavation, representing a wide range of species: large sauropods, smaller ornithischians, and the predatory animals that lived alongside them. It is, in short, exactly the kind of site researchers use to build a picture of what a Jurassic ecosystem looked like under normal conditions. What the bite mark analysis eventually revealed was that conditions at Mygat Moor were not normal and hadn't been for a long time. But a bone bed that size produces a specific interpretive challenge. When thousands of bones accumulate in the same location, the default explanation is flooding, a catastrophic event that concentrates carcasses from a wide area into a single deposit. Under that reading, the bite marks at Mygat Moor would simply reflect scavenging behavior, animals feeding on carcasses that arrived dead or dying. The marks distributed across bones in patterns consistent with opportunistic feeding. That explanation held until researchers began mapping exactly which bones carried marks and where on those bones the marks appeared. The distribution wasn't consistent with scavenging a flood deposit. Scavengers working a death accumulation feed on the most accessible, highest calorie surfaces first. Muscle attachment sites, joint surfaces, the areas of a carcass that decompose last and yield the most. But the marks at Mygat Moor appeared in places that don't fit that model. Lower in the skeleton, further from the muscle mass, on bones that would only be reached once everything above them was already gone. But the strangest detail wasn't the location of the marks, it was which species they were found on, and what that said about the state of the ecosystem at the time the feeding was happening. Toe bones are the detail that reframes everything else at this site. A predator feeding normally on a large carcass will work the thighs, the flanks, the neck, the areas where muscle mass is highest, and the caloric return justifies the effort. No predator working under normal conditions strips a skeleton down to the feet. The toe bones at Mygat Moor carry Allosaurus bite marks, and those bite marks are on bones from other Allosaurus. The predators were eating their own kind, and they were doing it completely, down to parts of the skeleton where there was almost nothing left to eat. One recovered bite was large enough that only a massive adult could have produced it, which means the hierarchy of the site wasn't equal. Larger animals were taking what they could from smaller ones, or from the dead. Out of 2,368 recovered bones at the quarry, roughly a third bear bite marks, and 17% of those are on large predatory animals. Drought was the context. Jurassic Colorado, 150 million years ago, during a period of resource scarcity, produced a site where the apex predator of the era left evidence of consuming itself. The teeth that built the Jurassic food chain were, under the right conditions, turned inward. We're about halfway through. If you're finding this worth your time, a like and a comment go a long way. Tell us which animal changed what you thought you knew. One apex predator stripping carcasses of its own kind down to the bones with almost no meat. That is what resource scarcity produced at a single site. From Colorado, the next case is a bone bed in Argentina, containing 7 individuals of the same species preserved together, adults and juveniles in the same geological layer. And what that composition leaves unanswered. In 1997, a team of researchers led by Rodolfo Coria and Phil Curry, working in the Huincul Formation of Argentina's Neuquén province, began excavating a site called Cañadón del Gato. The excavation ran across several field seasons. The material recovered gradually, building a picture that was not immediately obvious from any single fragment. What they found over the course of that work was a bone bed, a concentrated deposit of skeletal material from a single species, preserved together in the same geological layer. The animal was Mappasaurus rosae. Formerly described in 2006, a carcharodontosaurid theropod, closely related to Giganotosaurus and among the largest land predators that had ever existed. In life, it carried a long, deep skull with blade-like serrated teeth, adapted for slicing rather than bone-crushing. Powerful hind limbs that gave it reach and speed across the open terrain of Cretaceous South America, and a body plan built around delivering fast, forceful attacks rather than sustained grappling. The Huincul Formation itself records a mid-Cretaceous landscape of river channels and floodplains in what is now Patagonia, roughly 90 to 100 million years ago. A warm environment that supported some of the largest animals the Mesozoic ever produced. The Huincul Formation preserves a specific moment in Cretaceous South America, an ecosystem dominated by enormous sauropods, most significantly Argentinosaurus, an animal whose size estimates place it among the heaviest terrestrial vertebrates in the fossil record. Mappasaurus lived in that ecosystem and hunted in that ecosystem. The bone bed at Cañadón del Gato preserved not just the animal itself, but the question of how a predator, however large, could have functioned in a world containing prey that dwarfed everything else that had ever walked on land. But a bone bed is not automatically evidence of group behavior. Paleontologists are careful about this distinction because the alternative explanations are plausible and have to be ruled out before social structure can be invoked. Drought-related death accumulations can produce multi-individual deposits, animals of different ages dying in sequence around a dwindling water source, their bones concentrated by water movement into a single geological layer that looks, on the surface, like a group. Flooding can do the same thing, pulling carcasses from different parts of a landscape and depositing them together. The researchers at Cañadón del Gato had to account for both possibilities before the social interpretation could stand, but the composition of the deposit resisted the environmental accumulation explanation. The age distribution of the individuals, the mixture of adults, subadults, and juveniles, doesn't match what drought or flooding typically produces, which tends toward adults and older individuals with less mobility. And the species uniformity is harder to explain through environmental concentration, which usually pulls in whatever dies nearby, regardless of species. The evidence kept narrowing toward a question the environmental models couldn't answer. 7 individuals buried together, adults, teenagers, and juveniles, in the same formation at Cañadón del Gato. Preservation accidents don't produce age-mixed groups like that. What produces an age-mixed group is a social structure that kept multiple generations in close proximity during life, and the death event preserved that structure directly in stone. The question the site raises is what a group of Mappasaurus that large was actually doing together, and the answer is constrained by what was available to hunt. At 12.2 to 12.6 meters long and roughly 6.8 tons each, Mappasaurus was one of the largest predatory dinosaurs ever to exist. but Argentinosaurus outweighed it by an enormous margin, roughly the equivalent of 12 elephants compressed into one animal. Nothing in the Cretaceous could take Argentinosaurus alone. The group burial at Cañadón del Gato suggests the animals weren't just living socially, they were hunting socially, coordinating in a way that allowed them to pursue prey that was otherwise untouchable. Maposaurus didn't need to be the largest predator that ever lived. The group was what made the difference, and the group was what the fossil record preserved. 7 animals the group preserved in the rock alongside the question it answers. From the largest coordinated predators on this list, the next animal hunted alone, the largest carnivorous dinosaur ever found, with a body plan that took researchers most of the 20th century to correctly read, in a river system where the evidence eventually demanded a different reconstruction entirely. The Kem Formation of North Africa preserves one of the most unusual ecosystems in the entire dinosaur fossil record. During the mid-Cretaceous, roughly 95 to 100 million years ago, the region that is now the Sahara was a system of large, slow-moving rivers bordered by dense vegetation, an environment closer in character to a modern tropical river basin than to any landscape that exists in that part of the world today. The river channels teemed with enormous fish, coelacanths, lungfish, giant sawfish among them, while large dinosaurs moved through the vegetation along the banks. Spinosaurus aegyptiacus was first described in 1915 by the German paleontologist Ernst Stromer, who worked from material collected in Egypt by Richard Markgraf. Those original specimens were destroyed during an Allied bombing raid on Munich in 1944, leaving only Stromer's drawings and notes for the following 7 decades. The animal was effectively rebuilt from scratch when Nizar Ibrahim and a team of researchers formally redescribed it in 2014 using newly recovered Moroccan material, producing a reconstruction that differed significantly from anything previously proposed. The dorsal sail, a ridge of elongated vertebral projections running the length of the back, had been known from Stromer's original description, but the details of the skull, the limbs, and the overall proportions were substantially revised as new specimens came in. Spinosaurus aegyptiacus is the largest carnivorous dinosaur identified so far, 15 to 16 meters long, longer than T-Rex, with a body plan oriented toward the water rather than the land, in ways that took researchers decades to fully map. The early reconstructions treated it as a large fish-eater standing at the river's edge. What the anatomy actually described was something else entirely. But the fish-eater interpretation had a structural problem that the anatomy couldn't resolve on its own. An animal built for fishing doesn't need to be 15 to 16 meters long. Modern fish-eating specialists, herons, gharials, even the largest fishing crocodilians, achieve their hunting goals at a fraction of that body mass, because fish, however large, don't require a predator of that scale to subdue them. The size of Spinosaurus was always inconsistent with a diet confined to aquatic prey, and the inconsistency sat unaddressed in the literature for decades. But the anatomical picture grew more complicated as new specimens came in. The 2020 tail analysis produced a cross-section unlike any previously described in a theropod, flattened and structured with tall neural spines in a configuration that doesn't make sense for balance or display. The biomechanical modeling pointed to one function. But if Spinosaurus was built to move through water at speed, the passive riverbank model wasn't describing the right behavior, and the Kem formation contained more than just fish. The embedded tooth closes the argument cleanly. A Spinosaurus tooth physically lodged inside a pterosaur cervical vertebra is a record of an attack, not a coincidence of burial. The tooth broke off in bone during the strike, which means the force of the impact was significant enough to do that. Fast, targeted, violent. Spinosaurus wasn't standing passively in shallow water, filtering fish through a crocodile snout. The anatomy says something more specific. Nostrils positioned halfway up the snout to keep breathing during partial submersion. A paddle-shaped tail built for lateral propulsion underwater. Conical non-serrated teeth shaped for gripping rather than slicing. And a dorsal sail, over 1.5 meters tall, above a body that outmeasured every other carnivorous dinosaur on record. The bite marks found on land dinosaur bones at the same sites confirm what the pterosaur vertebra already implied. Anything that came near the water's edge was treated as prey, regardless of whether it flew, walked, or swam. The ecosystem around Spinosaurus wasn't a safe place to approach water. The ambush came from below the surface, and it came fast enough to trap a tooth in bone. The largest carnivorous dinosaur on record, its behavior written into anatomy built for speed through water. From that river system, the next animals are considerably smaller, but they left fossil evidence across 14 separate sites, and the condition of the raptor bones recovered at those sites contained a detail that the coordinated hunting model hadn't predicted. Dromaeosaurs are the group of theropods that popular culture collapsed into a single image after 1993. The fast, intelligent, coordinated pack hunter, stripped of feathers and scaled up to human height. The reality of what dromaeosaurs actually were is more varied and in some ways more complicated than the version that became famous. Deinonychus antihoropus was described by John Ostrom in 1969 from material recovered in Montana and Wyoming, and the paper that followed that description changed the direction of paleontology. Ostrom argued that the anatomy of Deinonychus, the stiffened tail, the large eyes, the sickle claw held raised off the ground during movement to preserve its edge, was inconsistent with the sluggish, cold-blooded reptile model that had defined dinosaurs since the 19th century. His work helped launch what became known as the dinosaur renaissance, the broad reassessment of dinosaurs as active, warm-blooded animals closer in biology to birds than to modern reptiles. In life, Deinonychus almost certainly carried feathers. Its close relatives preserved direct evidence of feathering and moved with the kind of speed and precision that Ostrom's anatomical analysis predicted. Utahraptor ostromizorum, discovered in Utah in 1991 during road construction near Moab, was the largest dromaeosaur known, 5 to 7 meters long, between 500 and 1,000 kilograms, carrying a sickle claw exceeding 22 centimeters, a predator closer in mass to a polar bear than to the dog-sized animals most people picture when they hear the word raptor. Both animals left fossil evidence that went beyond individual specimens. The question was what that evidence actually said about how they hunted, and whether the coordinated model held up when the bones were examined closely. But the coordinated pack model rested on an assumption that the fossil evidence never directly confirmed, that the animals found together at kill sites were working together intentionally. Multiple individuals of the same species near a carcass is consistent with pack hunting, but it is equally consistent with opportunistic group scavenging. Animals independently attracted to a kill site by smell, feeding alongside each other without coordination. Modern Komodo dragons do this. Crocodilians do this. The presence of multiple individuals at a feeding site doesn't distinguish between those behaviors without additional evidence. But at the Deinonychus sites, there was additional evidence, and it complicated the picture in a different direction. Some of the raptor remains carried fractures inconsistent with geological compression or sediment load, fractures that occurred during the animal's lifetime and partially healed, or that showed no healing at all, suggesting they happened at or near the time of death. Animals don't typically sustain broken bones from scavenging a carcass quietly, but the fractures weren't isolated to one site or one individual. They appeared across multiple locations in the sample, in raptor bones, at feeding sites, and the bones said they happened during the event itself, not before or after it. The 9-ton sandstone block from Utah tells the Utah raptor story in one preserved image, multiple animals of the same species, together with their prey, entombed in what appears to have been a quicksand-style entrapment event. They didn't scatter when the ground gave way. They stayed, or they were already too committed to the feeding to leave, and they died together in the same location. That's not individual predation. That's a group operating as a unit. Deinonychus tells a version of the same story across 14 separate sites in Montana and Oklahoma, each one showing raptor remains clustered around Tenontosaurus carcasses, and some of those remains carrying healed bone fractures consistent with trauma during feeding. The picture that emerges from both animals is not the perfectly coordinated wolf pack model that decades of film built. It's more complicated. Animals feeding in proximity to each other, sometimes getting injured by the prey or by the chaos of the feeding event itself. The cooperation real but not surgical. The bones say close contact predation was sometimes brutal for the raptor too. Raptors were predators, and the fossil record about how they hunted is more specific than the clean version. The next two animals aren't predators by any classification. Triceratops and Stegosaurus are herbivores, confirmed, not in dispute. What is harder to dismiss is the damage found in the bones of the predators that hunted them. Wounds that no predator anatomy in those formations could have produced. The standard framing of Mesozoic ecosystems places predators and herbivores in a simple relationship. Predators hunt, herbivores flee or defend passively, and the interaction ends with one outcome or another. Triceratops is usually placed in the defending category, an animal whose horns and frill were interpreted for much of the 20th century as primarily display structures, with combat capability treated as secondary or occasional. First described by Othniel Charles Marsh in 1889, Triceratops became one of the most recognizable dinosaurs in the fossil record within years of its initial description. In life, the frill was likely covered in skin with blood vessels running through it, possibly capable of color change for signaling, a structure more suited to communication than to physical protection. At 6 to 12 tons and up to 9 meters in length, with brow horns approaching a meter each, Triceratops was one of the largest animals in the Hell Creek Formation, sharing its environment directly with T-Rex during the final few million years before the end Cretaceous extinction. Stegosaurus occupied a different time period entirely, the late Jurassic, roughly 155 to 150 million years ago, and shared its environment with Allosaurus in what is now Western North America, also described by Marsh in 1877. During the competitive excavation period, known as the Bone Wars, Stegosaurus became iconic for the double row of large plates running along its back, now understood to have been richly supplied with blood vessels and likely used for thermoregulation and display rather than as armor. The thagomizer, the arrangement of spikes at the end of the Stegosaurus tail, was long assumed to be defensive without much direct evidence for how effectively it was actually deployed. Both animals left physical evidence in the bones of their predators. The evidence said the passive framing had missed something. But the display structure interpretation of Triceratops' horns had a structural problem that the physical evidence exposed. Display structures in large animals are built to be seen, not to absorb impact. They are often hollow or internally braced in ways that prioritize visual scale over mechanical stress tolerance. Triceratops' brow horns are solid, heavily cortical bones with an internal architecture consistent with load-bearing, the kind of construction found in structures that make repeated contact with hard objects. Hollow display horns don't survive direct contact with another large animal without fracturing. But the more diagnostic evidence wasn't in the horn material itself. It was in what the horns were leaving behind in other animals' bones. Circular puncture marks in predator bone require sustained pressure applied at a specific angle, and they aren't produced by glancing contact or passive defensive positioning. Stegosaurus presents the same problem. The thagomizer was modeled as a deterrent, a structure predators would avoid, but the spike material on recovered specimens told a different story. Impact scarring of that kind, spread across a meaningful proportion of the recovered specimens, doesn't accumulate on a structure that is never actually used. A Triceratops brow horn with a healed T-Rex bite mark on it, and T-Rex bones with circular punctures matching the dimensions of Triceratops horns. Both sides of that confrontation survived it. Triceratops wasn't prey that occasionally got fortunate. It was an animal physically capable of inflicting permanent skeletal damage on the apex predator of its era, and the fossil record confirms that it did. Stegosaurus makes an identical point in a different time period and a different formation. The Allosaurus tail vertebra in a Utah museum carries a 3-centimeter hole punched clean through the bone, the edges showing months of healing tissue, the dimensions matching a Stegosaurus tail spike exactly. Roughly 10% of recovered Stegosaurus tail spikes show lifetime impact damage, not edge chipping from accidental contact, but the kind of impact scarring that comes from striking hard objects repeatedly. The tail was being used as a weapon on a regular basis. And the Allosaurus vertebra says at least some of those strikes landed with enough force to drive a spike through bone and leave it there long enough for the wound to partially heal. The herbivore classification is accurate, but herbivore and dangerous are not mutually exclusive categories, and the fossil record from both animals makes that plain. Triceratops and Stegosaurus left permanent evidence in the bones of the animals that hunted them. The last two animals on this list built their weapons differently, one growing an entire body into armor with a tail club whose force calculations placed it in a category no other herbivore matched. A specimen called Zool carries heel damage in a location and at an angle that rules out every known predator in the Hell Creek Formation. Ankylosaurus magniventris is the most heavily armored dinosaur in the fossil record, first described by Barnum Brown in 1908 from material recovered in Montana. It entered the literature as the definitive example of passive armored defense in the dinosaur record, an animal that had, over millions of years of evolution, traded speed and agility for near-total physical protection. The osteoderms that covered its back and flanks were not attached to the skeleton, but embedded directly in the skin, meaning the armor moved with the animal's body rather than sitting rigid above it. At 6 to 8 meters and over 6 tons, it was built from the ground up around protection. Fused osteoderms across the back and flanks, a low center of gravity, limbs that sat under a body more reminiscent of a tank than of any conventional reptile. The tail club, a fused mass of bone at the end of a stiffened tail, has been the subject of biomechanical analysis that produced specific force calculations, and the numbers placed it in a category of weapon capable of causing severe skeletal damage to large predators. A specimen called Vastata, recovered from Montana in 2014 and formally described in 2017, is among the most complete ankylosaur specimens ever found, preserving not just the skeleton but much of the soft tissue impression of the armor arrangement in remarkable detail. Pachycephalosaurus wyomingensis occupied the same formation, the Hell Creek, alongside T-Rex and Triceratops, and was built around a completely different structure. Described in 1943 from Wyoming material, it was a bipedal herbivore of modest size relative to its formation mates, distinguished almost entirely by the skull dome, a thick mass of solid fused bone rising from the top of the head with no internal air spaces, pure bone all the way through, sitting atop an otherwise unremarkable skull. The dome's function was debated almost from the moment the animal was described. Researchers examining dome specimens in detail found damage patterns across the surface, but what made those patterns significant wasn't their severity, it was when they started appearing in the animal's life. But the tail club on Ankylosaurus presented researchers with a directional problem. The weapon swings laterally, side to side, not downward. A large predator attacking from above, which is the most common predatory approach to a low-slung armored animal, would receive the club's force across its lower legs and feet, not across its dorsal surface. The biomechanics of the swing are well suited to that target. But the Zool specimen's damage wasn't on the lower legs or feet. The healed marks were on the flank, the side of the body, at a height that no predatory attack from above could produce. The geometry didn't fit any known predator in the Hell Creek formation. But the Pachycephalosaurus evidence pressed the problem further still. The dome debate had centered on whether the skull was used for direct cranial impact at all, with some researchers arguing the bone structure was better suited to flank contact than head-to-head collision. The damage patterns found across dome surfaces aren't consistent with flank contact, and the distribution of that damage didn't align with any of the functional explanations the existing debate had proposed. The Zool specimen carries the evidence in its own armor. Healed damage on the flank, consistent in shape and angle with a strike from another ankylosaur's tail club, means the weapon wasn't reserved for predators. Ankylosaurus was swinging a structure mathematically capable of shattering a T-Rex tibia against members of its own species. And the healed wounds confirm it happened, and the animal lived. The club was built for intraspecific combat as much as it was built for defense. Pachycephalosaurus closes the entire picture in a different register, a 10-inch dome of solid bone covered in pitted scars, healed punch-outs, and infections severe enough to have killed some individuals weeks after the impact event is not the anatomy of an animal that occasionally bumped heads. The damage begins appearing in juveniles before sexual maturity, before any territorial claim or mating competition could explain it. These were young animals already practicing the same form of skull-to-skull impact that adults used, which means the behavior was learned early and sustained throughout life. Some of those infections killed the animal that survived the impact itself. The dome didn't always protect. Sometimes it absorbed enough damage to cause a slow death weeks later, from wounds too deep inside the skull to be visible from the outside. A species that built its entire social structure around inflicting and absorbing brain trauma, starting in youth, continuing into adulthood, leaving permanent scars in bone, is not a creature defined by passivity or herbivory. The weapons were the body, and the body was always ready to use them. That's the record, as the fossils left it. If you enjoyed this, a like helps this channel keep making content like it. And if you have thoughts, an animal we missed, something that surprised you, leave it below. We'll see you in the next one.